You're joining Julia User Group Munich and a Code and Share session where I'm always inviting other speakers. Today, we are going to look into control systems and have with us Fredrik Bagge Carlson. He's the maintainer and developer of the go-to package in Julia for designing control systems, and he's going to give us an introduction today. I myself am Stefan Sam. A couple of months ago, I founded a Julia consultancy called Julien. And as always, if you have kind of some ideas where you need Julia consultancy, please just drop me a line and we'll see whether we can pimp Julia at your place. That would be lovely. Okay, so Fredrik is with us. He is from Sweden, so having again an international setup and working for Julia Computing, also in a remote setup. His background is in robotics and systems control, so he's really the person you should ask all your deep questions for. Thank you for being here today with us, Fredrik. The stage is yours.
Thank you, Stefan. Thank you for the initiative to this talk. Let's see. Let me know if the size of font and so on is okay and you can see the screen.
Yes, I can see everything. A little bit bigger would be still welcome, I think.
Yeah, let's see.
Yeah.
Yeah, all right. So this is the outlines for tonight's talk. I will introduce myself and then I will introduce the subject of control theory just very briefly. So for those of you who have no background in engineering or in control. And then, of course, I will talk about what Julia Control offers. So Julia Control is the GitHub organization where we host the control systems and a few other packages. So who am I? As Stefan said, my name is Fredrik and I live in southern Sweden. I got both my master's and my PhD from the University of Lund, the city where I live now. And my background, as Stefan said, is in robotics and control and system identification in particular. And of course, I enjoy writing software toolboxes. I've been writing them in Julia since 2016. And you can find my GitHub here if you're interested. And currently, I work at Julia Computing in the simulation team. But tonight here, I represent myself. So if I express any opinion, or if I say something stupid, that's all on me. Okay, so control. What is control really? So in an essence, it's making dynamical systems behave in a desirable way, and preferably automatically. So we typically say automatic control. And there are some very typical examples. So for instance, you might want to use a cruise control of your car. So control the speed of the car automatically. Or you want to keep an airplane in the air, and then we call it an autopilot. Or it's a manually controlled airplane, but it's unstable, like a modern fighter jet. Then you typically need a control system to stabilize it. Or maybe you're sitting in a room that has a comfortable indoor temperature. And that's probably some kind of controller that is maintaining that comfort level. If it's very simple, we call it the thermostat, but there might also be a more advanced climate control in your building. And these are the most common examples you think about, perhaps, but actually control systems are really everywhere. So the human body and all biological systems really have a ton of controlled systems. So one example might be if you eat some carbohydrates, your blood sugar will go up. But the body has a very tight control of the blood sugar. So it will fairly rapidly release insulin in order to try to regulate the blood sugar level. But there are also feedback systems, control systems in electronic amplifiers. Financial markets is another example. So there are control measures you can take to influence the financial market, such as the interest rate. It's perhaps the most typical one. But also, if you operate a server, such as a newspaper online, you might have a queue of requests. People want to look at your news. And if that queue gets too long, then you need to spin up additional servers or additional machines. And that is also a form of a controlled feedback system. But control is often a hidden technology in the sense that it's always present, almost always present in engineering systems, but you never really talk about it. The only time you talk about it if it fails, and then it often fails spectacularly because control is often mission critical. So if a control system goes down, it can spell disaster actually. So the electrical grid is another example. If a control system fails there and the frequency is not maintained, then you have a disaster, you have a blackout. And why do we need control? And in particular, why do we need feedback control? And I would argue that the fundamental reason is that we have uncertainty. And uncertainty really comes in everywhere in engineering. So we don't have a perfect knowledge about the world and about the state of the world. Any model we might have is always going to be inaccurate. And if we measure things, those measurements are often noisy. And we also cannot measure everything either because it's physically impossible or it's too expensive to measure. And measurements are noisy. And even if we have a very good model of the world might change. And then we don't have an updated model of the world. And that is an additional source of uncertainty. So this is the fundamental reason that we make use of feedback control. And the magic of feedback, this is an expression I've taken from a professor that started the control department at the university where I graduated. It really is magic in a sense that, so feedback, first of all, it means that you're making a measurement and then you act based on the measurement. So you feed back the output of the system through a sensor. And the magic of feedback is then that feedback allows you to make accurate, high-performance systems out of inaccurate components. And we will see an example of this here. So a very early example of feedback we have in vacuum tube amplifiers. So vacuum tubes, of course, were used for early telecommunication. But the problem with the vacuum tube is that it's very non-linear. And also the amplification changes with temperature. And it also changes with might change with the lifetime of the component. So how can you make a nice linear amplifier out of such an unreliable component? And the answer, of course, in this case is feedback. So if G here, this little box or this little block, it represents our vacuum tube. It has an amplification gain of G, and we send in a signal R. We can think of R as a sinusoidal signal, perhaps. And then G is amplifying that, and on the output we have Y is G times R. All right, but then if this gain here is varying, then the amplitude of the output will vary even though we have the constant amplitude on the input. And if G is some kind of nonlinear dynamical system, then we will have a distorted sinusoid on the output. And if you try to send in a voice, so if R is a time series that represents a voice recording, then it will just sound very bad on the output after we have amplified it. But if we connect now this block G in a feedback loop, so we take part of the output and we feed it back, we might multiply the output with a gain, and then we add it with a negative sign. So we subtract it from the input here. We call it negative feedback. Then if we write down the relation we have and we rearrange slightly, we see that Y is now this expression here. It's a rational function where G appears in both the numerator and the denominator. But the key thing here is that if G is very large, so if the amplification is large, then we can ignore the 1 here. And it says G over G, so that those cancel each other, and the amplification will just be 1 over K. So then we can control the amplification of this system by choosing the gain K. And if this is an electronic system, this might be some kind of a resistor or a passive electrical circuit back here. But the thing is, we can choose K. And key to this is that even if G varies, as long as it's large, the gain of this circuit is constant. So we have taken a circuit which is nonlinear, time varying, and horrible, really. And then we introduced negative feedback. And now we have a constant linear gain, as long as the original G is very large. So this is an example of where we have taken an unreliable component, introduced feedback, and now we have a very reliable system as a result. And if you're more interested in this and the history of feedback control, I would suggest this video by Carl-Johan Åström. It's a link here to a YouTube video you can check. Another example is we use control to suppress disturbances. So if you have a room, you can imagine the room where you're sitting now. Hopefully it's around 20 degrees Celsius there. And you would ideally like it to stay 20 degrees, even if several people enter the room. So each person is about 100 watts of power, heat generation. But also someone might open a window. And then, of course, if you're in Sweden right now, then the room will be cold. But also during the day, maybe the sun is shining in, and that, of course, adds power to the room. And we can depict such a system here with this little block diagram. So we have a room. So that's some kind of dynamical system represented by differential equations, for instance. And the output of the room is the temperature. And we can measure that. So we introduce measurement feedback. And then we form the error here. So we have a reference temperature, maybe 20. And then the controller here, K for controller, it looks at the error, reference minus the actual value. And then it sends in a control signal, we say, into the room. So that might be your radiator or your air conditioning unit going to work. And this D here is a disturbance that enters, in this case, on the input. So this might be the sun is shining in and adding power to the room. And if we write similar transfer functions like we did before, the temperature is some kind of transfer function times the reference, and it's another transfer function times the disturbance. And these transfer functions here are really algebraic representations of differential equations. So if the system is linear, it's a set of linear ODEs, we can represent the system using the Laplace transform as an algebraic function here. So R is really a function of the Laplace variable S. But the key point here is that we can choose K here. K is the controller and we choose it. So we can choose to either shape the response to a disturbance, or we can choose the response to a reference, or we can try to make it so that both of these transfer functions look okay. And if you want to shape them both independently, then you can add another box here that you also choose with a shaping of the reference. And then you can shape these two functions the way you want. And control theory is really about designing K in this instance. Control theory, of course, deals with a lot of other things, such as determining the model for the room and analyzing the stability properties of this feedback loop. But fundamentally, we are interested in designing a controller, sometimes we call it a compensator, K, that makes the overall system behave in a desired way. All right, and now I've said a lot of nice things about feedback, but there is a caveat, of course, that whenever you close a feedback loop, you might actually turn a stable system unstable. So here we have kind of an arbitrary linear system. It's a third order system. It's represented by this rational function in the Laplace variable S. And if we send a step input into this system. So it starts by being 0, and then suddenly at time equals 0, it's 1, and then it's constant. We see that the system has a response. It swings a bit back and forth, but then it settles out at 1. But if we close the feedback loop here and introduce feedback with a gain k, we see that at first the gain is reduced. But if we keep increasing k, now we have reached some kind of a never-ending oscillation here. And if we keep increasing it, now actually the system appears to blow up, that the oscillation is getting bigger and bigger. And this is a risk you almost always suffer in designing control systems. You might turn the stable system unstable, or you might fail to stabilize an already unstable system. So in control theory, we are very concerned with analyzing the stability properties of a feedback system. And Julia Control is, of course, an attempt at providing such tools in the Julia ecosystem. So before we introduce Julia Control, I will just make a brief note about linear dynamical systems. So when we talk about control theory, very often we are quite happy with just using linear systems, even if the true system is nonlinear. And the reason, so linear systems correspond to a linear differential equations. It might be a set or set value differential equations, which you can write on a matrix form. And a nice thing about them is that you can analyze them algebraically using the Laplace transform. And if you have a nonlinear system, then typically we linearize that system. And the reason this often works very well is that when we do control, we are very often interested in regulation. And that means that we want to keep a variable at a fixed set point. So the temperature controlled room was such an example, that we want the temperature to be 20 degrees centigrade at all times. So if you linearize a potentially nonlinear system around the operating point 20 degrees, the control system is responsible for making sure that we stay close to the point of linearization. So that's why linear methods often work very well. But if you take a robot, for instance, so one of these industrial robots that might have 6 or 7 degrees of freedom, that is a very highly nonlinear system. And the whole purpose of the robot is usually to move around. And then linear methods do not work as well. But with just a tiny splash of nonlinear theory, nonlinear ingredients, we can fall back onto linear methods after that. So Julia Control is really focused on linear control systems for this very reason. And another reason is that the nonlinear world it's kind of open-ended. It's everything that is not linear. So there is an infinite surface area to develop methods for nonlinear systems. But the ControlSystems.jl is the main package for linear control systems. And it's very similar in spirit and scope to the corresponding MATLAB control system toolbox. And it provides support for all the common things you might see in such a control toolbox. So transfer functions and state-based systems. We can simulate time responses. So we can calculate frequency responses, and you can design your LQR and LQG controllers and Kalman filters and so on. All of that stuff is of course included. And there is also a paper that describes the toolbox with some more technical detail on this link if you should be interested later. But as I said before, Julia Control is currently not for nonlinear systems. And it's not for what we typically call open loop optimal control. So when you compute in advance a trajectory for a system that is in some sense optimal. For instance, if you would like to send a rocket to the moon, you will probably apply some form of optimal control for that. So this is not what Julia Control does. There are lots of other very competent packages in the ecosystem that does this. But this is open loop as opposed to closed loop usually, in the sense that so open loop means there are no feedback, no measurements. You compute everything using a model. And so the toolbox was actually started in early 2016 by Jim Christ. But since mid 2016, there is a team of us that originated from the Lund University Control Department. So here we have Mattias Fält, Albin Heimerson, Olof Troeng, and myself. So we have been the main developers of the toolbox since then. And every now and then we get some contributions from the wider ecosystem as well. And if you feel like contributing, we would be very happy to welcome your PR into the toolbox. So about toolbox.
Fredrik, let me ask you a little question, because you've written currently it does not support these other parts. Are you planning to support them in the future?
Probably not in the main toolbox. And one reason is that non-linear control is extremely open-ended, in the sense that depending on your system, you might need vastly different techniques to design and analyze the non-linear system. So then the scope of the toolbox would grow infinitely. So I think a more reasonable approach is to have special purpose packages that solve one aspect of the non-linear design or analysis. And many such packages do exist already. But it would be very hard to find a suitable scope for a control systems package that includes just arbitrary non-linear stuff. So if you want to solve open loop optimal control problems, there are already very competent packages in the ecosystem. So we don't really need to incorporate that into control systems. And if you want to simulate non-linear systems, then you can either use differential equations directly, or you can use a modeling tool such as Modeling Toolkit. And we do intend to provide an interface to Modeling Toolkit so that you can go between Modeling Toolkit systems and control systems in case they are linear. So that is a well-defined scope that is well worth to support, I think. Does it answer your question?
Yeah, thanks.
Yep, thanks. So, do we offer something unique in this toolbox? And I think it's the same as with other software written in Julia, that if you take some care and write your code so that you are generic with respect to number types, you can automatically support a whole host of interesting use cases that are not supported elsewhere. So in our case, all systems can take any kind of coefficients. So typically you design maybe using floating point 64-bit values, but you can also put in a symbolic coefficient. So here's an example here. It's not runnable code, it's just to show. The paper includes, and the supplementing material to the paper includes runnable code for this example. So you can use symbolic coefficients. You can also use some form of uncertain parameters that represent maybe a probability distribution. You can use arbitrary precision numbers such as big floats if you want to simulate with extreme precision. So that is fairly unique, I think, and it's very useful. We will see an example of using uncertain parameters for control design later in this presentation. But you can also use stuff like GPU arrays. So here is an example where we use the CUDA package, and this example, of course, is silly because the arrays are very small. But if your arrays were much bigger, and you would like to simulate this system, then this is actually much faster. And there are a whole research project of designing control systems tools for GPUs, but in Julia it comes for free, so we don't even need to worry about it. You just get it for free. So that's actually quite remarkable. And another aspect we have is delay systems we have support for. So MATLAB obviously has support for this also, but among open source control toolboxes, I don't think there are any others that support this, because it's a bit hairy to support simulation of time delay systems. But we have an internal representation that is described in the paper, and then we make use of a delay diff EQ package from the differential equation ecosystem that allows us to simulate this very nicely. And of course, all of that interacts with, so you can put big floats into that, and it goes through the differential equation solvers, and you can solve this to extreme precision if you would be interested in that. So now I will show a first example of how you use the toolbox. And if you have done control design before, maybe in MATLAB, or if you have used the Python control toolbox, everything should look very similar. So they are very similar in their look and feel. And the system in this case is a first order system. So this is a first order transfer function. And then there is a time delay. So e to the power of negative s tau, it implies a time delay of tau seconds. And time delays are nasty from a control perspective, because they pose fundamental limitations on the performance you can achieve. And we all probably have struggled with the time delays in our lives. So a very typical example that speaks to people is when you take a shower. And in the beginning, the water is cold, and you increase the temperature. And then it takes a while before you notice the change. And before you have noticed the change, you might have increased the temperature so much that you actually burn yourself. And then you have to dial it back. And that is a problem with a time delay, because if you had noticed immediately the change in temperature, you would never dial it up too far to burn yourself. But a very common approach to designing a controller for such a system is to use something called a Smith predictor. So essentially, we can recognize in the diagram here, this is the regular path with a nominal controller C0 and the system here, and a feedback path. But then we introduce this additional feedback path where we have a model of the system and we have a time delay. And if the model of the system is perfect, then this part here will actually cancel this part, and the controller will only see a model of the system without the time delay. So then you can design your controller as if there was no time delay at all. And that makes it much easier to design. But of course, if you get a disturbance affecting the system, then it will take a while before you can counteract that disturbance, because you can't really act faster than the time delay. So here is a lot of code, but we will go through it slowly. So the very first line here is we create the model of the system, what I call P0. So this is the system without the time delay. So I represented it up here as a transfer function. And this is the corresponding state space version. So I call SS, and I enter the system parameters. I could also call TF for transfer function and enter the corresponding transfer function parameters. The next step is to design a nominal controller. So the controller I call C0. And I do that using something called pole placement. So I decide the bandwidth I'm interested in, 2 radians per second. I specify my desired relative damping. So 0.7 is common for a fairly well damped system. And then I get the controller out of this command here. So this will now be a PI controller for proportional integral. So it's a simpler version of a PID controller.
Fredrik, there's one question in the chat.
Yep.
Thanks for asking. Where's the control in the delay system? So we've seen in the little picture in the diagram that K is not there.
Yeah, sorry about that. K in this case is this whole block, including C0 and this path here. So all of this inner feedback loop is K. So I'm sorry about using a different letter here. In control systems literature is a bit ambiguous. Sometimes we say C for controller and sometimes K for controller, but the entire controller is this entire loop. So this controller has a model of the system built into it. So P0 here is a model of the system. All right. So the next step here is to add the delay to the nominal plant. So we say the time delay is 8. We create the delay component and we multiply it by the nominal system. So this is now the full system. And then we form this inner loop here. So the inner loop is a feedback between C0 and these two elements. So that would be this line. And the function feedback is common in control tools. It allows you to form the algebraic equations for the feedback interconnection in a very simple manner. So this is exactly what you saw in the block up here. Delay -1. So this is, yeah, it's the negative of that actually, because there is a, why is that? Yeah, because feedback assumes a negative delay, sorry. This function assumes that you have a negative delay, but now we have a positive, so we need to switch them. Then we might simulate this in the time domain. So here I create 2 different systems and I concatenate them in a vector. So this is the feedback loop from the reference to the output. And this is the feedback loop from a disturbance to the output. So the first system is from R to Y, whereas the second loop is from a disturbance that enters here and exits here. And then we say LSIM. So LSIM is a MATLAB legacy word. It stands for linear simulation. We simulate this system and our input is a function of time. And the first system has a constant input 1. And the second input has an input which is 0 until the time hits 15. And then this would be a Boolean value. So this would be 1 after time 15. And we can look at that plot and we see here the first 8 seconds, there is nothing. Then we see a response. So this is the response to the change in the reference. And it's somewhat well damped, some overshoot. And then after 15 seconds here, there will be a disturbance entering the system. And then it takes 8 seconds again until we see something. And then the value shoots up. But then after 8 seconds, we manage to suppress the disturbance and we're back down to the reference. We can also look at this controller in the frequency domain. And that we do here. So we call the function Bode plot. So if you have any experience with the analog electronics or control system design, you're familiar with Bode plots. They show a linear system in the frequency domain. So we can form the theoretical predictor that the controller contains, and we can compare it to an ideal predictor. So an ideal predictor would be the negative time delay. And that corresponds to that you can see tau seconds into the future. So most of the time we can't see into the future. Sometimes maybe we can because we know how signals would change in the future. But we might as well compare the response of our Smith predictor to this ideal predictor. And we see that the ideal predictor has a unit gain, flat, whereas our Smith predictor has kind of a jagged gain like this. And the ideal predictor has an increasing phase like this, whereas our actual predictor has kind of this interesting phase curve here. And then the last plot is the Nyquist diagram, which is familiar to those who have control background. And here we are interested in looking how many times this open loop response and circulates this red point here, -1 in the complex plane. And if it encirculates this in a particular way, the closed loop system will be unstable. So these are all very common control systems tool, which you expect to be present in a control system toolbox. And this is how they work. They work exactly the same as they work in MATLAB, more or less. So that should be very familiar if you come from that direction.
One beginner's question, just to understand a bit the terms.
Yep.
There you said this is setting up a nominal system.
Yeah.
Can you shortly explain again what the nominal stands for?
Yeah. In this case, the nominal system is the system without the time delay. So nominal is unfortunately a very overloaded term. I take it to mean what you have without all the extra stuff. Okay, so the nominal in this case is just this transfer function 1 over s plus 1. And then if you add the time delay, then you have the complete system. And then you use a model here of the nominal system inside the controller.
Thanks a lot. Yeah, that helps.
Yep. All right. So the next example we will look into is a bit more elaborate. And here we will show one of the strengths of Julia, really. So in this case, we will try to design a controller using optimization. But in this case, the plant, so the system we are trying to control, P. The nominal, once again, nominal system is this transfer function. It's second order. And it's on a special form where we can read zeta here is we call it the nominal damping. And omega is some kind of a bandwidth. And we want to control that using a PID controller. So this here is a Laplace representation of a PID controller. We have a proportional term. We have an integral term. So in the Laplace domain, an integrator is 1 over s. And a derivative is, of course, then s. And we have a derivative term. And then we have a second order low-pass filter to filter the measurements, because measurements are always noisy. And if we differentiate something that is noisy, the derivative will be extremely noisy. And if we then put that noise on the input to the system, then maybe we risk damaging the system. So in the case of a robot, if you feed back measurements from a accelerometer, so accelerometers are known to be very noisy, and if you differentiate that, you get an extremely noisy input, and that input is what you send to the motors of the robot. And if you have too much noise there, you will actually hear the motors will start making a noise. They will get very warm and they will wear out prematurely. So filter design is critical when you design a control system also. So we will go through step by step here. First, we will start by designing a controller for the nominal system without any uncertainty. So this system might represent something like a mass that is attached to a spring. And that sounds academic and silly, but position control systems are usually very well modeled by this kind of transfer function. So if you move a motor very slowly, it looks like a double integrator. But if you move it very fast, the gearbox actually becomes a bit flexible. And when you reach your destination, you might have some oscillations due to this flexibility. So the gearbox behaves like a spring. So this is actually a reasonable model of such a system. So if we just create the system here, we say transfer function. We choose some values for the parameters p, omega, and zeta. So omega of 0.3 is it's fairly common for a position control system. It's quite poorly damped. If zeta is 1, we have a perfectly well damped system. And if it's 0, it's undamped, meaning that it continues to oscillate forever. Then we create the transfer function. We create this function here. And I immediately convert it to a state-space system. And the reason I like to convert everything to state-space system is because a transfer function is a rational function of 2 polynomials. And polynomials of high order are very poor from a numerical perspective. So it's good usually if you can to convert them to state-space systems. So we do that. And then next, here I just create a vector of frequencies so we can plot a frequency domain representation. I choose an initial guess for the controller parameters. So this is the proportional gain, the integral gain, and the derivative gain. I just arbitrarily set them to something. Then I create my PID controller. I just pass in the parameters there, and I create the second order low pass filter here with a time constant of 0.05. All right, I form the closed loop system. So I call the function feedback. And this forms the block diagram I showed before with a feedback connection. I also form a different system, which is called the sensitivity function. And this function is of interest to control designers because it tells you how well you are able to suppress disturbances. So we will look at it, we actually plot it here, but I will come to it later. So we are interested in keeping this function low for low frequencies. So if there is a low frequency disturbance, we want to completely eliminate that. But for high frequencies, we can't hope to suppress those disturbances. But then we want to limit the magnitude of it, because if we have a very high magnitude, we might be sensitive to model errors, and then we might actually end up with a poorly performing control system. The next step is we call the function C to D. So this stands for continuous to discrete. So we take a continuous time model representing differential equations and turn it into a discrete time model that represents difference equations. And the reason we do this is so we can simulate without having to use a ODE solver. So if we didn't do this, it would still simulate. It would use an ODE solver, but it would be slightly slower. And we want to perform an optimization here, so it's significantly faster if we do this step. And then step here is a short command. It performs the simulation where the input is a step function. And we see the result of this step here in the leftmost plot. It starts at 0, and then it swings a bit back and forth, and slowly it starts to reach 1, but it doesn't actually reach 1 within the time here, 15 seconds. If we would step a bit further, we will see it will slowly work its way up to 1. And if we simulate even further, hopefully. What did I do here now? It's thinking about it. Anyway, it would eventually reach 1, but it's going very slowly. Yeah, here we see it reached 1 after a while. But we see that it has a very horrible response. It oscillates quite a lot, and then it's quite slow in reaching 1. So this is a very poorly tuned control system so far. The next plot here, I call the function Bode. So I calculate the Bode magnitude of the sensitivity function over the frequencies I've specified. And then I plot that, and we see the function in the middle. So this is the magnitude of the sensitivity function. And this is the frequency axis, the x-axis. So for low frequencies, we see that the sensitivity function is low. That means that if we have a disturbance of a low frequency, for instance, a constant disturbance, we would be able to suppress that, meaning that that disturbance will not cause an error in our output after a sufficiently long time. And we also saw that if we let this simulate for a long time, we reached our desired reference of 1. But we also see that we have a peak here. It shoots over 1. And that means if we have disturbances here on these frequencies, then we will actually amplify those disturbances using our feedback. And that is of course not desirable. We want to suppress disturbances. But this is a trade-off. It's fundamental. If you press down this function in some places, you will have you will have the complementary sensitivity function actually will jump up in other places. So you can't have infinitely good performance everywhere. There are trade-offs, but we would like to make sure that this peak is not too high so that we don't amplify disturbances unnecessarily. And to the right here, we see the Nyquist plot. of the open loop system. And we know that we want to make sure that this blue curve does not encircle this red point, because if it does that, then the closed loop system will be unstable. So here we see that it does not, in fact, encircle it, but perhaps it's a bit too close. And the reason we don't want to be too close, because we know the model is actually bad. Models are always bad. They are inaccurate and so on. So the actual curve might be somewhere else. This is just the best guess. So we want to stay quite far away from this point to make sure that we have sufficient robustness against model errors. So this was all with the initial guess for the controller. So now we will try to tune those parameters. And we will do that by optimization in this case. So here we plot the same system as before is blue, but now we have optimized it, and we will look at the optimization code later. But here we see that now the response is very fast. There are no oscillations at all. We reach the reference of 1 very fast. And we see that the sensitivity function is very low for low frequencies, and the peak is reduced. So this is quite a nice design. We also see at the Nyquist plot that now this orange curve is much further away from the critical point here, -1. So we are quite happy with this design for now. So how did we achieve that? I started by specifying a constraint on the peak here of the sensitivity function. So we see a dashed line. The sensitivity function may never be above 1.2. So that gives you a fairly robust system. Then I have a helper function here that calculates the same things as we saw in the code above. We take in parameters. I exponentiate them so I can optimize in logarithmic space. This ensures that the parameters are always positive. Then I create the controller just like before. I create the closed loop system and the sensitivity function just like before. I additionally create another transfer function, and this is the magnification of measurement noise, because I want to also limit the maximum gain of this one, so I don't feed too much measurement noise into the system. And then I perform a simulation here. So this is just a helper function. The other function is our cost function. It calls this helper function, and then it calculates the maximum of the border diagram of the sensitivity function. So it calculates this peak point here, which initially is here. And then I just add a very simple constraint here. So I say if the maximum sensitivity is higher than the constraint, then I pay a very high penalty here. So this is a poor man's version of a constrained optimization problem. And then my performance cost is I want the response, the time domain response, y, to be close to 1. And I penalize the absolute deviation from the desired response. So this is penalizing the distance between this curve and 1. And then I have a similar penalty on the maximum magnification of the noise here, CS. And some weights to tune the optimization problem. Then I convert my initial guess to a log space, and then I just call optim.optimize with this cost function. And then this function is just to plot. We don't need to go into it, but this function just draws these plots. And we see that the response is very nice. We have fulfilled our constraints, and we see that we are outside the constraints in this plot also. All right, but this was with a nominal system without any uncertainty. So what happens now if the parameters of the system are actually uncertain?
Fredrik, wait a second. We have 2 further questions again by Michelle. Thanks for asking. First one is, how do you figure out the system response in the first place?
So how I get the model of the system?
Yep. Second question is, how are you sure the optimization finds the real optimum?
Yeah. Thanks for those questions. So here I make use of a model of the system, as you point out. So this is my model of the system here. I have chosen the parameters. So there are multiple ways of obtaining such a model. Either you go and physically measure things such as masses, lengths, and you write down the physical laws of motion or whatever physical insight you have and derive the differential equations. And that is one way of obtaining a model. So that we typically call it a white box model because you know everything about it. Then sometimes you don't have any physical insight because the system is just too complicated, or maybe it's very complicated physics with viscous air resistance, which is proportional to the somewhere between the square and the yeah, it can get very complicated, right? And you don't want to write down the physical equations. Then you might resort to something we call system identification, which is you can think of it as some kind of machine learning, but it has existed since the 60s at least. And it's a way of obtaining a linear model or a nonlinear model for that matter, which you can use for control design. So I will actually get to that when I come to this here, system identification. But you need a model to make use of these methods, and there are multiple ways of obtaining them. And then the next question, can you remind me again?
Yes, sure. So how are you sure the optimization finds the real optimum? And then there's another question by Jan. How long does the optimization run?
Right. Yeah. So for complicated controller designs, you cannot know that you reach the optimum solution. So the problem is typically non-convex. It's also non-smooth because of the constraint. But you can verify if the result you get is satisfactory or not. So typically you have some kind of design goals, desired design goals, and if you meet those, you're happy. You don't necessarily need to reach the global optimum. For a low order problem like this, you can just you can actually use global methods if you would like to. But in general, it's hard. You don't know if you found the global optimum, but you know if it's good enough or not. And the duration it takes to solve this problem is almost instant because it's so small. When we get to the uncertain parameters later, it will take slightly longer, but it will be a few seconds, so it's not too bad. All right, so now we will introduce the uncertainty. And to do that, we make use of a package, Monte Carlo measurements. It provides a special number types that represents a probability distribution with a number of samples. So they are called particles. And in this case, we make use of 50 samples. So here is a helper function that creates a suitable distribution, normally distributed. So now I say that P, the parameter P, PU for uncertain, we think it's 1, but it's plus minus 30%. And the damping, maybe it's, we don't know exactly what it is, but it's between 0.1 and 0.35. And the same here for the resonance frequency. We don't know exactly what it is. We have a 5% uncertainty, roughly. And then I create the system just like before, and I might plot it. And now we see that we have quite the distribution here in the response. And we see that some of the realizations actually violate the constraint. So we had a constraint here, the dashed line, that we were not supposed to be above 1.2 in the maximum sensitivity function. But now we can't actually guarantee that the true system is below that. And the same with the Nyquist plot here. We see that some of the orange points are actually inside the circle. But no problem. We perform the optimization again. And this time we use robust optimization. So we see here, if I just send in now the parameters with an uncertain system PU, we get an uncertain cost value from the cost function. And the optimizer from Optame will not really like that. So I redefine the cost function slightly here, where I instead of this here performance criteria, it would be an uncertain value. I take the mean of that. And then I take the mean of the constraint of the noise amplification also. And then if I call this cost function instead, I get a regular number without any uncertainty. So this cost function now I can optimize. And if I do that, we see that now we get a new set of parameters. And now all of the curves here are below the constraint. And the price we paid for that is that the response here is slightly slower. I don't know if you can see everything at once. Whoops, sorry. Sorry about that. What happened? Here. Now we can see both. We see that the response was slightly faster up here, and it's slightly slower up here. But in return, we get a more robust system that is further away from the critical point here. All right, then we can look at the parameters also. Before we optimized with uncertainty, we got those parameters. And when we used robust optimization, we got slightly lower numerical values. So that's a slightly more conservative, less aggressive controller, but it's safer in some sense. All right, so this was a naive way of performing robust controller design. There are much more sophisticated ways, but hopefully it was quite straightforward. We just put uncertain parameters into the system, and we just called a very straightforward optimization routine from Optame, and it just worked. And I think that's quite beautiful. And for simple systems, you can actually make good use of this. All right. Any more questions about the robust optimization? No?
Fredrik, can I ask you to zoom in again a little bit?
Yes, of course. Let's see here.
Thank you.
Yeah. So that was everything about control systems, the package control systems. There is an additional package called Robust and Optimal Control, and it's an extension to control systems. It just contains more. It has uncertainty modeling using something called mu analysis. It has something called named systems, so the inputs and outputs and state can be given names. There is some more functionality to design LQG controllers and H-infinity design and so on. But I'm not going to go into that here. Instead, we will have a look at system identification. So now I come to answer the question about how do you obtain the model. So system identification is both an art and a science, really, about estimating models for dynamical systems. And we have a package, Control System Identification, that does exactly that. And it's focused on what we call black box linear models. So it's a linear model without any additional physical insight. You just specify, I want the following order, for instance, order 3, and then it gives you a model, a linear model of order 3. And it contains model methods in both time and frequency domains. And we will see a very simple example here where we estimate the model for a temperature system. So a very simple model is a first order differential equation. So T here is the temperature, and T dot is the time derivative. We have a time constant. So that's related to how well insulated your house is and how much thermal mass. If you have stone walls, you will have a longer time constant. And then the B here is related to your radiator, and C here is related to the surrounding temperature. And this is a linear model. We can write it as a transfer function on this form. We see it's a first order system. It has one parameter in the numerator and one parameter in the denominator. So we can set up this system here and simulate it. So I chose the time constant 10. So you can think of it as 10 minutes perhaps. W is a frequency vector for plotting. And then I discretize it once again so we can simulate it very fast. So this is the transfer function here. Then we sample some input. So when we want to perform system identification, we want to make use of a nice input signal to the system. So we really shake the system. We want to expose all of its properties. And the way we do that is to use a signal that contains a very wide frequency spectrum. And a chirp signal is such a signal. So we see here the input here in the bottom. It's a square wave, but in the beginning it has a low frequency, and then it increases the frequency, and in the end it has a very high frequency. And if we send this signal into the system, we will really expose all of its properties. So linear systems are completely characterized by their frequency response. That's a very nice theoretical result, which is practically very useful. And if we simulate the system here, we see we get some output. It's a slightly smoothed version of the input, and it's smooth because the system is kind of a low pass filter. And then we have added measurement noise also. So here the measurement noise is actually quite high. So it's a very bad thermometer if you want. So here is just some code to simulate, add measurement noise, create an identification data object, and then we plot that. So before we estimate the linear system, we should really, we often forget, but we should look at what's called the magnitude square coherence. And that's a non-parametric way of asking the data, can the data be accurately characterized by a linear system? And if that is the case, the coherence is close to 1. But if there is a non-linear behavior, or if there is a significant amount of noise, then the coherence will drop. So here we see that for low frequencies, the coherence is very high, but then after a while it drops off. And that's because our chirp signal only contains a maximum frequency, right? And this frequency, we have reached it here, and above that, we don't have any high coherence because there was no input power in that spectrum. So if we fit the model using this data, we cannot hope to rely on the model above 1/10 hertz because there is no data to estimate. So we don't know how the system behaves there. So that's very important to keep in mind when we have estimated a model. But nevertheless, we may proceed. We specify here the order of the system. NA, we know it's a first order system. So NA is 1. And NB here is the number of parameters in the numerator. And then I use 2 different methods. So one is called subspace identification. It estimates a state space system. And the other one is called pseudo linear regression. It estimates a transfer function. And these are the 2 estimated systems. We see that the time constant here. Now this is in discrete time. So it's not 1/10 like you might expect. But if we convert it discrete to continuous, we see that the time constant here is almost 0.1. And which is corresponding to, the eigenvalue is 0.1, meaning that the time constant is 10, 1 over 0.1. We might plot the Bode diagram. So here there are actually 3 curves. It's the true system in blue, and then the 2 estimated systems, but they are so accurate, they are on top of each other. And the reason they are so very accurate is because we cheated a bit here. We simulated the data. We knew it was a first order system and there were no non-linearities or anything like that. So it's easy to estimate. And we might also perform a time domain simulation. And here we have also 3 curves, and we see they are very close to each other. And we might simulate using the original data here. And once again, we see the response looks like we would expect. So in practice, in real life, system identification is much more difficult because no systems are truly linear. You need to spend a lot of effort designing the input to the system when you do experiments. For some systems, in particular, if they are unstable, you must perform identification in closed loop. So if you want to identify a model of a quadcopter, you must actually have something that stabilizes the quadcopter, because if you don't have that, it will crash and then you get no data. But system identification becomes harder if you have closed loop. You introduce, when you introduce feedback, you feed measurement noise into the control signal, and you might run into biased estimates and so on. So there are lots of interesting theory to dig into there if you should be interested in that. And here is a code to plot. But this is one example of how you might obtain a model you can use for your control design. And very last, I would like to mention there is a package called Symbolic Control Systems. So there are some additional tools to work with systems if you have symbolic coefficients. And it can also generate C code. So if you have a discrete time system that corresponds to a discrete filter, So you can generate C code to filter signals through that, and that can help you implement your controller or noise filter if you have designed a linear noise filter. All right, summary then. So Julia Control tries to offer really a feature-complete environment for everything related to linear control system. So analysis, analyze the robustness, the stability properties of closed loop systems, design estimators for control systems, and I think we do a reasonable job at that. There are lots of things we would like to add, in particular when it comes to uncertainty modeling and robust design. So that development is taking place in this package, Robust and Optimal Control. So check it out if you're interested. Lastly, I would like to say, please don't hesitate to reach out. If there is an issue with the package, open an issue on the issue tracker. If you have a longer question, more in depth, you can reach out on Discourse. So I follow Discourse, and so do many of the other contributors. There is also a #control channel on Slack where you can ask quick questions. And we also welcome pull requests, including if you have written a tutorial. So if you are, for instance, a teacher at the university or something, and you have written some control tutorial or examples, feel free to add those to the documentation. We would be happy to expose those. And if you use the system or the software as a user, be sure to say hi and mention what you like and what you don't like, because I myself am a user, but I am only a single person with a single viewpoint. So it would be great to get to hear other people's experiences and see if you have run into trouble, something that is inconvenient. Perhaps it could be very easy to fix it for you. And with that, I would like to say thank you for listening.
Thank you, Fredrik, for being with us today and for the awesome presentation. I just shared the source code link you already provided in Discourse.
Yep.
So for everyone who would like to replicate what we've seen today, the Pluto notebook is online. Thank you also, Fredrik, for preparing this.
Yeah, my pleasure.
Cool. We have time for other questions, and there's already one question. Jan mentioned that he's working on nonlinear arcs models in MATLAB, and he asked whether there are any plans or other packages you are aware of that support such kind of systems.
Yeah, actually, nonlinear ARX models, I've gotten this question on several occasions. The control system package, system identification package, does currently not support it, but it wouldn't be too hard to support it, at least in some limited scope, I think, because we make use of, in particular in the prediction error method, which is what I assume you would like to use for nonlinear ARX models. We make use of the prediction error method, and then we make use of auto differentiation. So if you would enter nonlinear feature functions there, it wouldn't be much problem to support it because the gradients come for free, essentially. So if you would be interested in adding such support, feel free to reach out, open an issue, and we can discuss, and we can maybe add something like that.
That sounds very awesome.
Let's see, I see a question. How can system identification tell me that the system is linear or not? So for that, I recommend making use of what I call the coherence function. So I will show it again here. The coherence function is a frequency domain method. You just take the data. So this data object contains the input and the output, and it performs Fourier transforms of the data, and then it calculates what's called the magnitude square of coherence. And if that is very close to 1, the system is very well described by a linear model. So for a linear system without any noise, it will be exactly 1. And if it drops below 1, if it drops significantly below 1, it means that there is something that is not exactly a linear relation between the input and output. And that might be either that the system is nonlinear, or it might be that you have a lot of noise. And if there is a lot of noise, of course, the output is not explained only by the input, it's also explained by the noise. So that another way is, of course, to fit the linear model and see if the linear model is good at predicting and simulating. If the simulation is very close to the data, then the linear model obviously works quite well. But the coherence function is very principled in the sense that you get an estimate for how well a linear model fits as a function of frequency, and that's quite useful. Let's see. Unfortunately, okay, that was Jan about the ARX, yeah. Yeah, so I said I expected prediction error method, and the reason I said that is because the prediction, if you implement the prediction error method, you can very easily turn off the prediction feature, and then you have simulation error minimization. So if you implement prediction error method, you get simulation error minimization for free, essentially. So I have implemented a prediction error method in the package. Actually, I'm doing quite a lot of work on that just the last few days. So that will be greatly improved soon, I think. But by just turning off the predictor part, you get the simulator. All right. Have I missed any questions?
No, that have been the questions in the chat. Thank you for answering them. I think they are very happy about the answers.
Yeah, thank you.
Are there some more questions? Please just write them or raise your voice.
Yes, about the documentation. The documentation, yeah, to understand the package, if you have any prior experience with control system packages such as MATLAB, the documentation should definitely be sufficient. If you are new to control, then the documentation will not be sufficient. Then you would need a control book alongside. Of course, if you're a complete beginner, I would go with a beginner's book, such as feedback systems with Åström and Murray, perhaps. If you're slightly more advanced, I like a book by Skogestad. I can't remember what it's called. I think it's called Multivariable Feedback Systems or something like that. It's a good book. I can write it in, I can share these references in the control Slack or something like that after the talk if you're interested. But the documentation assumes that you are familiar with the subject of control. Yeah, there is a question about the overlap with the DSP package. So we do make use of the DSP package for some functionality. Unfortunately, not all too much. We have our own transfer function types, and they have their own. I have a pull request that has gone stale since a couple of years ago, implementing an interface to connect the two. We have talked about making use of common core functionality, like types in particular. The problem there is that someone needs sufficient amount of time and reason to implement that, I think. And also, we have slightly other demands of our types than the DSP package do. So we couldn't straight off use the same types anyway. So unfortunately, we haven't really spent the time to integrate them so far. But otherwise, the DSP package has some functionality for frequency domain analysis, and they have much more functionality for filter design, for instance. So if you want to design filters, the DSP package is definitely the way to go. Toolboxes integrate optimization packages. Yeah, so one of the beauties, I think, with Julia is that packages work quite well together, even though you don't spend time making sure they do. So in the system identification package, I make use of Optim, for instance. It's a general black box solver for nonlinear optimization, and that works beautifully. Machine learning, yes, maybe. Most of the machine learning frameworks make use of reverse mode automatic differentiation. And unfortunately, many of the RD packages are still, they don't really accept generic Julia code. So you will have a hard time trying to differentiate through our functions in reverse mode. Reverse diff sometimes works, not always. Zygote is quite difficult to make use of, actually, because Zygote is very limited. They don't support mutation and try-catch statements, so it blows up quite often. But we have made use of the package together with these frameworks in kind of many custom ways, and that works quite well because packages tend to work together for free in Julia. So try your luck. If it's something you need from our side that we could accommodate, we might be able to do that. But otherwise, it usually works quite well just firing off and mixing packages without explicitly supporting it. And then there is a question, what is reception of Julia control in the industry? And how likely is it that engineers drop MATLAB in favor of Julia? So MATLAB is ahead of us, definitely. They have been in this game for, I don't know how many years, but it's probably at least 30 years. For most common control design workflows, the Julia control toolbox works quite well and is quite well battle tested. For slightly more elaborate, especially uncertainty modeling, if you want to model stuff like time varying parameters, MATLAB is way ahead. We don't have that so far. It would be cool to have it. It's just a matter of resources. We don't have it so far. Will engineers drop MATLAB in favor of Julia? Maybe, maybe not. So there are certainly people who do use it in industry. And that's quite encouraging. MATLAB is expensive, so that's one reason perhaps not to use it. But if you already have MATLAB, if you've used it for a long time, then perhaps not. If you do a standard run-of-the-mill control design, I don't think that we will see a switch because it's not worth the time probably for a lot of people. But people who are interested, people who want to mix in machine learning, more elaborate solving of differential equations and so on, maybe solve on the GPU. There are interesting things to get in the Julia ecosystem, and that does draw people also. Let's see, danger of having different teams work in different control. Yeah, I'm not sure if there are so many different teams. Oh, you mean, okay, so some people at workplace working in MATLAB and some working in Julia. Yeah, that is probably not desirable. So if you already have MATLAB, then probably you will stick to that, I guess. Unless you have some other reason to switch to Julia. But if you are in a workplace where you do not have a MATLAB license, then definitely consider the package and evaluate it. It's free. There is documentation. Check it out. If it works for you, it's brilliant. MATLAB system identification is fairly old. Yeah, I don't think they have seen super much updates recently. And I think there is only so much you can do for linear systems. I mean, I still follow the literature. There are new research coming out. But for the vast majority of basic cases, the linear methods that exist in MATLAB system identification toolbox and also in control system identification, they take you quite far. So that's perhaps why they have spent time on more modern stuff like deep learning and so on. Post reading material about system identification with feedback. Yeah, so that is an interesting problem. Feedback creates a problem for a lot of identification methods. I will try to collect some material. My go-to, if you haven't read it, would be the book System Identification Theory for the User by Lennart Jung. It's probably the most widely cited work on system identification. It's quite readable also. And as he said, theory for the user, it's user-oriented. It's a brilliant book. It's thick, but it's very elaborate, and it's fairly easy to read. So I recommend that. System Identification Theory for the User. Yeah, thank you, Stefan. It's by Lennart Jung. So when it comes to the control system identification package, if you have a feedback system, I recommend you make use of the prediction error method. If you make use of subspace identification, at least the methods we have in this package, they will be slightly biased under the influence of feedback, but the prediction error method is unbiased in this case.
Thank you. One further question from my side.
Yeah.
The version of control systems is already at 0.12. Are you already looking forward to a version 1.0? And what would be kind of your missing things you still want to get until 1.0?
There are some very minor things left. We might change the internal data layout on some arrays that are produced when you calculate frequency responses and so on. And that would be a breaking change. We would essentially output the transpose of what we do now. There are also maybe some names we would like to deprecate, but that's essentially it. So version 1.0 is quite close. I can't tell you in time, but in amount of changes, it's quite close.
Awesome, awesome to hear.
Let's see a question here.
A user report.
Yeah. Yeah, so thanks for sharing your experience, Johnny. This is something I hear quite often, also from people in the Python community, that Python and MATLAB also has a lot of large packages that provide you with what we call cookie cutters. So they do the standard things very well, but if you want to do something that is not standard, it's very difficult to shape the functionality into to suiting your needs. So Julia, if you are a power user and you're willing to look around the ecosystem for tools and mix and match, as you say, you can usually get quite far. And especially when packages interact so well, and when you want to derive gradients, you get that almost for free, and sometimes with just minor adjustments using automatic differentiation. You can really get quite far with what we have in Julia, but at the same time, it sometimes requires you to be somewhat of a power user. So, but with time, hopefully we will fill some more gaps while keeping the power user friendliness. Another thing I see is that MATLAB provides a lot of graphical apps, graphical user interfaces. But if you have Pluto, I can go back to this little plot here where I showed the slider. Where did I have it? Let's see. Here. Here I have produced a little plot. So I create a system. I plot the step response. And K here, this parameter K, it's set by this slider. So here I say bind K to a slider. And then I automatically have an interactive app. And I can, of course, make this app as complicated as I want. I can introduce many sliders and text boxes and so on. And then with extremely minor effort, I have made an interactive graphical user interface. And that is remarkably powerful if you think about it. So the user can themselves create this. It's absolutely trivial in Pluto. You can do it also in Jupyter notebooks. But also, if you can provide, say, Control Systems could provide some apps like this, where we just set up more or less a skeleton to show the user how it's done. But then the user can themselves modify the code here. So I can add stuff freely to this code and add another plot and maybe plot some additional things and so on. And that is something that if you take a graphical app from a software you buy, you can usually not modify that app. So the tool provider must make sure that it has all the features you could possibly need. And that means that the app will be very bloated because everything you don't need is just noise. And sometimes stuff you do need is not there because they hadn't considered your particular case. But if the app is a Pluto notebook where the code is exposed, you can just modify the code and make it suit your needs. And that is something I'm looking forward to see in the future because I think it's remarkably powerful.
Great. We are approaching 8 o'clock.
Yep.
So sounds for me like perfect timing. There are also no new questions coming up in the chat. So I want to thank you again, Fredrik, for being here today with us.
Thank you,
it was
Stefan.
An awesome presentation. Really also easy to get for someone like me who is not that deep into control systems.
I'm glad to hear.
I thank you very, very much also for your examples here and there, which illustrated the ideas in more easy to grasp manners.
Yeah, thank you.
Then I also thank everyone who joined today. Again, we have been a big group. I wasn't expecting so many. Thank you for being there and for all your interaction and questions. It was an awesome experience. I wish you all a good night. Then I stop the recording.
Thanks. Bye.